Hey guys, welcome to our channel again. Thank you for coming. Today we get extremely good tutorial about a really interesting subject, which is light, and today we're going to talk about the two-slit experiment, and I brought the two-slit experiment here. Here it is. We're gonna do it. The two-slit experiment. I got the laser, I got the slit, I got everything we need. Before we're gonna dive into the equation and calculation and do the experiment ourselves, I want you to see a short video that's gonna sum up the ideas of the two-slit experiment, okay? So I'm gonna press the button here and then a video will show up and you're gonna see it and come back, okay? Ready? I press it.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing.
In the beginning, God created the heaven and the earth, and the earth was without form and void, and darkness was upon the face of the deep. And the Spirit of God moved upon the face of the water. And God said, "Let there be light." And there was a light. And God saw the light, that it was good. Guys, since the ancient time, people were so curious about light, about the phenomena light. What is light? Okay? And two major scientists start to investigate that idea. On the right side, we have Newton, with a lot of achievement in that time. Okay, we're talking about the 17th century. And Newton said that the light that we actually seeing is particles that move through the eye. Like you saw in the video, some particles that come into the eye. But on the other hand, okay, there was another guy named Huygens. And Huygens says something completely else. He said that light is actually, the light that we are seeing, is actually a wave. Phenomena that change in time and space, getting stronger, weaker, and come to our eyes. He said that is a waves. And people don't know what to think about it, okay? And then comes the cool experiment that you saw. The two-slit experiment, okay? Thomas Young, the man that decided to do this experiment on light, Thomas Young, decided to do this experiment. And the idea of light as a particle was out of the picture for a while, and we're not gonna talk about it in this class, okay? But Einstein, after that, brought this idea back, okay, with the photoelectric effect, okay? But we're not gonna talk about it in this class. We're gonna talk about Thomas, okay? So what's happened when you're taking light, put it into a two-slit, okay, a hole and another hole. What do you see? I'm gonna show you exactly because I got the experiment here. So let me take the camera off the stand so you're gonna see it. Perfect. So now you see my room. So this is the board, and right now You guessed it right. This is the two-slit experiment. So here I got a laser, and here I have some barrier, and the light gonna cross the barrier and have two slit to go outside, okay? So let's show you this idea. So I push the button of the laser, okay? Oh, here it is. Here's the laser, and the laser go through this one. Let's put it in the middle. Oh, wonderful. What you gonna see on the board? Oh my God, you see it? Crazy. This is crazy, okay? We actually see that the light behave like a wave, okay? Let's zoom back and let's continue. Let's go back to our tutorial. Okay, perfect. So hold yourself in place. You know, it was a cool journey with the camera. Okay. Perfect. You are safe, back in place. Let me see that you see everything clear. Perfect. Back to zoom. Nice. Okay. So that's what we're seeing on the board. Let's try and draw what we actually. I'm gonna bring it back. Okay. Let's keep it. This was here in this line. Okay. I close the laser. Perfect. We're gonna talk about that soon. So what's happened actually, okay? So I took the laser beam. Here it is. I got a really fancy laser, a red laser. So let's take the red. This is the laser. Okay, here it is, the laser. Let's find out where's the middle of this story. Okay, the middle is somewhere here. Okay, so okay, so here I got a laser, a red laser, and if it's red, I know its wavelength, right? I open Wikipedia, I can see the wavelength is 650 nanometers. Nano mean very small. How small? 10 to the minus 9. That's the idea. Close the laser again. Okay. So I know the wavelength, and here what I'm doing, I'm putting here a slit. Okay, and here the laser cannot, let's do it more visible. So the laser actually shining in all direction, okay? Let's emphasize that it's shining in all direction. You want to go everywhere, but what I'm doing, I said, you're not gonna go from here, okay? And you're not gonna go from here and not gonna go from here, but you can go from this part. So the wave can actually get away from here and shine any point on this line. For example, let's say this random point P or position, okay? So the light beam gonna hit it here and another gonna hit it here, okay? That's what we actually saw, and this is happening to every point. The light right now can get out only from these 2 points. How I did that? I took a laser. This is, for example, the beam. Okay, this is the beam of the laser, and I have here this board, and here I didn't let the beam to cross. Okay, and what is the length of this? The length of this is called D. This distance, this one, this distance from here to here, it's D, and I measure my D. My D is actually 2.3 times, also really small, minus 4 meters. That's what I have for D. This one here is D, this line, okay? The distance between the two slits. Okay, perfect. So now I want to ask you a question. And also the distance from the wall, this is the wall, to my laser, which is over there, called L. This is the length, okay? This is the size. If I would have a meter, I put the meter and boom, okay, and can measure it. Perfect, okay? So let's clean the board, okay? And I want to ask you a question, okay? My question to you is, is the laser over here, its properties K and omega change, or they stay the same before and after? Okay, that's a question to you. So I want to tell you that omega, the angular velocity, is actually equal to 2 pi f. Okay, and 2 pi f I can take f and set the wave equation v equal f lambda. I can actually state it in another manner. I can say that f it's actually that v sorry, okay, let me start all over again. Okay, so I can state lambda in other way. I can announce that k equal to 2 pi over lambda, right? I can put it here, and then I'm gonna get that the wavelength is 2 pi v over lambda, okay? And I know k, this is k, and omega, the angular velocity, is actually, if I'm gonna put this one, right, as k, so the 2 pi are gonna cancel each other. V of the speed of light, I know it's c, and this is equal to ck, okay? It's just a warm-up. I just want to say, okay, that the property does not change. The laser here and the laser there is the same laser, okay? You have the same frequency. Frequency does not change, okay? Never change, but the wavelength can change if I change materials. For example, here it's L, and here it's air, okay? So lambda not gonna change from here to there. But if here was a water or glass or stuff like that, yes, the wavelength was changed, and we're gonna talk about it in the last question, but I just want to warm up and tell you about it. So we finished talking about this idea, and now let's go back to our experiment and talk about the real interesting stuff, okay? So the real interesting stuff is talking about what is the electric field. Let's see, adjust the camera, perfect. So what is the electric field? Sorry about that. What is the electric field at that position, at P? Okay, that's really interesting. So let's talk about that. So what is E over there? So E at location P, so P at any time is equal to what? It's equal to 2 contributions. That's what I want you to remember. One contribution is from this laser, and the other one for that laser. There's 2 beams that in the same place, okay? So it's actually equal, let's do it in red, okay? 2 contributions. One is the first beam, okay? Which is gonna be this one. And this is the second one. So E1 at location P at any time, and 2 at location P at any time, right? Vector, vector, everything is vectors, okay? And what is this light? Okay, so we know how light wave behave. So this one is actually equal to E0, the amplitude, some sinus wave, right? At what? At the location K multiplied by R2. Sorry, I wrote 1 and 2, so this is gonna be 1. Okay, sorry about that. It's gonna be 1 minus omega t. And what is R1? R1 is this distance. Okay, is distance from this point to this point. This is R1. Okay, the distance that the light go through. And this is gonna be R2, the distance from here to, you see, it's a long distance, but they're different, they're not the same. Okay, it's really important point. Plus the same thing, right? E0 sinus K, it's the same light, so the K is the same. R2, it's a different length that the laser went through, right? So this one went going, aha, I got it. This one going, a little bit more, ha, got it, okay? So minus omega t, it's the same one. And now I want to sum them, okay? I can use science, this one, this is the second one. So I'm gonna use how to sum up sines, just easy trigonometry. And this one is equal to 2E0, okay? That's what happens when you sum 2 sinus. Here you're gonna have sinus of what? Of the average. I'm gonna sum the argument of 2 of them and divide it by 2. So that's gonna give me the K is the same, R1 plus R2, okay, minus 2 omega t divided by 2. Perfect, okay? And this one gonna be multiplied by what? This is the interesting stuff. but what it's gonna be multiplied. So this one is a cosines, I'm gonna multiply it the same one, and just don't wanna cancel this beautiful drawing right now. So this one is cosines of the subtraction of each other, okay? So the subtraction of each other is, so things gonna fall out, right? Because this minus that, okay? So the same stuff, the stuff that are in common, gonna fall out. So what's gonna fall out? Yes, exactly. So this one gonna fall out. So what we're gonna stay with? We're gonna stay with K and delta L divided by 2. Okay, so what is delta R? Delta R is actually the difference between L2 to L1. We talked about the trajectory, okay, the path that this one is going and the path that this one is going is different. They are not the same. So you're gonna have your delta R, and this is super important. Why this is so important? Look at it. If we're gonna look at this equation, this is the result, what is the electric field, which present light, okay, electric field and magnetic field. Remember, they are moving perpendicular, well, it's really hard. They are moving perpendicular to each other, right? But that's what present the light. So if we're gonna look at that idea, and we're gonna say, okay, this is changing in time. Sometimes it's 0, sometimes it's maximum, sometimes, but it's always there, okay? It's always there. Maybe in a specific time you don't see it, okay? But most of the time it's there. But what's happened here? Here, it's not relevant to time at all. It's only relevant to space. It's relevant to the distance between these two beams, which is different from every point. This point, for example, in this point, this delta R are gonna be 0 because it's gonna be in the center. They're gonna be mirror of each other. They're gonna be look the same. But in every other point, look, like they different. One is bigger than the other. Okay, that's the idea. So this term and of course the properties of the laser, which light, which wavelength I'm using, also gonna change this. Okay, so this is really important. Okay, so let's find this delta L. Okay, let's see what is it. So what is delta L? So I want to draw this one, and let's try to do it here. So I know it's really small, but I want you to see something. This one and this one, maybe they are not the same distance, but they are really close in the distance. For example, if I'm gonna put here a 90 degrees angle, okay, I put here let's do it bigger. So this one, okay, this is L1, it's continued to L1, and this is, okay, and this is L2, it's continued to R2, but I put here a 90 degrees angle, okay? This one is really long, this one is really long. So this angle, it's really almost 90 degrees, okay? It's almost 90 degrees. This is 90 degrees, that's for sure. So I can say that the distance, this is from here, R1 is starting. So R1 is starting from this point and going all along. But here, it's almost L1, right? So like I said, this L1, from here, it's like R1, approximation. So this distance is actually delta L. Okay, so I can find delta R using this one. And let's call this distance D, which I gave you before. This is the distance between the holes. This is a hole here. From here the laser going out, and from here the laser going out, right? So I can actually calculate what is this delta R, okay? So delta R is actually, let's see, so let me clean this one, okay? So delta R, if I'm gonna declare as this angle as the sinus theta, as a theta, so I can do this over that. So this is a sinus theta equal delta R divided by D, and which means delta R is D sinus theta. Perfect. So we found the term from dr in the equation, which is the interesting part of the electric field. Okay, perfect, really good. And why I could do this approximation, I could do this approximation, okay, due to the reason that I say that L, remember L was the distance between the light and the board, right? So L is so big, so long, the beam need to go so far away from this distance D between the two slits, right? So that's the reason I could take this assumption. It's almost 90 degrees, okay? And if I'm gonna do another trigo, so I want you to, let's write here delta R equal to D sinus theta. Just I want you to know that this is this, okay? So, but if I'm gonna take another cool approximation, if I'm gonna draw this one again a little bigger, okay? So here it is, this, and we talked about some point here. So this one is here, this one is here, and we declare that this is 90 degrees, this is almost 90 degrees, this is theta. So if you're gonna look this one at this line, we can see that this point, this is not a laser. This laser, this is laser, this is laser, this is laser, but the one in the middle, let's do it in other color, let's do it in green. Oh, this one is not working. Let's do it in blue. So this one, sorry, this one is actually, it's really hard to do this kind of things without, okay, so this is the middle, right? So this is the middle line. Okay, this is L. And right here, it's for getting accents in the middle. Let's really put an effort to do it. Better configuration of that. Okay, perfect. And let's do the slits here and here. So this is distance is D between them. And I want to go to some position. Let's say this one and this one, and from here this one. Perfect. Okay, so I want to go to this location, and we said that this angle is 90 degrees. You see how close it's look to 90 degrees? Okay, it's not 90 degrees, but it's almost 90 degrees. Okay, and this angle here is theta. And if I'm gonna draw a line, okay, a red line between the point and the middle of D, okay, it's gonna look something like that. Sorry, something like that. So this angle here in between, this angle, okay, is actually also theta. Okay, and you can prove it, okay, just to imagine of two triangles, and you're gonna see that this is the same. So if I'm gonna do this one, I can actually state this point using theta. Okay, so that's the idea I wanted to tell you. So we're gonna get to that idea soon. Okay, and perfect. Okay, so this is also theta, and this one is also theta, the angle from here to here. This is L, this is the distance from there to there. Perfect. Okay, so then my question to you is, okay, so when I'm gonna see the most shiny light, okay, we're gonna see the most shiny light. Of course, the answer where we're gonna see the shiny light is when this term don't kill the electric field, right? This one is maximum, is 1 or minus 1. It doesn't matter the direction of the electric field, up or down. But when this one get to maximum, okay? So let's clean the board a little bit. It's really hard because I need this all the time, okay? But we're gonna do it. So I wanna declare, okay, that cosines of K, and remember our delta R is D sinus theta, okay, divided by 2. I want it to be equal to 1. And when that's happen, so if this is a cosines, so we're gonna start from 1, okay, and cosines is actually starting from the top and dying out, right? So this is cosines, start from the top and dying out, and come to the line and die out. So this is cosines. So where this term is 1, okay, it's 1 and 0. Here it's minus 1 at pi. Minus is also fine with me, okay, minus 1. Here 2 pi. Here 3 pi. So I can see the pattern. What's the pattern? I need the argument, this part of the cosines, to be equal to some natural number multiplied by pi. That's what I need. N pi equal to this term, k d sinus theta divided by 2. That's what I needed to be 1 minus 1, okay? Perfect. So, we can actually put, I don't like this pi here, so I can actually put instead of k what? 2 pi over k. And this one gonna kill this one, and these two gonna die with these two, and I get the d sinus theta, okay, divided by lambda equal to n. Okay, interesting. And sorry, not n, let's call it n, big N. Okay, why? Because I'm looking for maximum. Okay, so I wanted to use the letter big N, capital N. Okay, so I got big N. And so what is the angle which I'm gonna see the maximum? This is, we talked about that this is called theta, right? So if I look at a position, it's another way to talk about it. You see the camera, you look right at me. So if I open the angle of the camera, this is the theta, right? So what theta that I need to look from the center that I'm gonna see? There's a maximum. There's a maximum, okay? So what is the theta? So let's take it out. So the theta that I'm gonna see maximum is actually lambda m divided by d. Okay? So you found all the maximum that you're gonna see. Okay? And if I'm gonna open the laser, I want you to notice, okay? I want you to notice that you actually can see a lot of points. Here it is. You see it? It's moved a little bit, but you see that this is, see that there's a lot of points. This is like maximum, 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 and then it's dying out until it's become completely dark. Okay? Another way to talk about it is actually asking what is the distance. This is the middle here, okay? Not this one, okay? Let's shift a little bit. But what is the distance? Let's close this one again. So what is the distance I need to measure to find x, to find p? What is the x of the maximum? Okay? It's another question. Let's do that one. Okay, not the angle, what is the x? So if I look at this triangle, let's take it out, this triangle. So I have also, this is xm, this is L, and this is theta m, right? So I can do tangents. You see it? So I can say the tangents of theta m equal to xm, which I want to find, divided by the length, the distance on the board. So I know that, and I can do another assumption. It's, we're talking about a really small angle. So I want you to see. My room is approximately 3 meters on 3 meters. So this one is from the camera is actually 3 meters away. Okay? So I want you to understand that this angle is super small. Like here it's already dying out. You almost don't see here. Maybe I can see a little bit, but it's really, this is the maximum angle you can find. So we're actually talking about really small angles. So tangents in really small angles is always sinus theta divided by cosine theta. Okay, this one is actually going to 1 for small angles. So I can state that tangents theta behave like a sinus theta in a small angles, right? So I can actually clean this one and say because it's a small angles, I can use theta n. You see what I see? So I can actually change and put this one over here. So let's close the laser. And where is it? So let's clean the board. So this one I can change it to put xm over L, right? And then I'm gonna get the final result, which is xm is actually equal to m multiplied by L lambda divided by d. Perfect. So right now I know all the places that are gonna observe maximum. Okay? You know what? Let's calculate it. This is, I don't know, 3 meters. This is, how much we said is it? 2.3. 2.3 10 to the minus 4. And this L, this lambda, we said it's 65.9 to the minus 9, right? So you can calculate it and maybe comment below. Calculate what is this value, and I guess, okay, let's see if our calculation is right. So you should get the distance here. You should get the distance from the maxima. This is the middle of the laser. This is the middle. So you should get this kind of distance. And let me measure it. This one is approximately, I know it's around 75 millimeters, which means it's not even a centimeter. Okay, so I guess this is less than centimeter. This distance you're gonna get here. Okay, put here 1. This is gonna be the first maximum you see from the middle, this distance. If you're gonna put 2, you're gonna get this distance, which is gonna be approximate a little bit more than 1 centimeter, and then you're gonna get the third one, the second one, the first one. You see, that's what happened. And you can put your minus, and then we're talking about the one over here. I don't know if you see, it's so small, but that's the idea. Okay, so calculate it, comment below, let me know how much you get it and what was actually the distance here. Okay, perfect. So let's move on. Where is it? Here it is. Okay, perfect. So let's move on. So as we talked about the maxima, you see that I also got some dark place. See that here in between this and this, it's fading out, and at the end, here there's no light. No light at all. Well, where I do blue? No light, 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 no light. Okay, so let's find these locations. So the idea gonna be the same, okay? Let's clean this one. Right now, I don't want it to be 1. I want it to kill the electric field, okay? Don't bring it back alive. So how are we gonna kill this motherfucker, okay? So we're gonna say, okay, this is the cosines. This is the cosines, okay, perfect. And cosines, we talked about that, it's looking like this. But we want to kill. We want here, 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 here. So where this is happening, so this is happening at 1 multiplied by pi over 2. This happened at 3 multiplied by pi over 2. This location. This location is at 5 multiplied by pi over 2. And this location is 7 multiplied by pi over 2. Okay, I got the pattern. Okay, I see it. So the angle, this theta, should be theta that actually it's an odd number multiplied by pi over 2. That's what I need to do. Okay, so okay, let's do it. So k d sinus theta divided by 2 must be equal to, if I want to kill, to something pi over 2, something that multiplies pi over 2, and I want it to be odd. How I write in a mathematical way odd number? I just do an even number and I fuck him up. Okay, so I'm gonna do 2m, okay, small m, because we're gonna talk about minimum, okay, minima. 2m, which is even number, I'm gonna fuck it up. -1. Ha! You're gonna be odd. Okay, so that's the idea how I do it. Okay, and now I can actually I can get rid of the 2 and the 2. K, I can say again it's 2 pi over k, so this pi and this pi dying out. And what do I gonna get? I'm gonna get that sinus theta, and this is a specific theta of a minimum, okay, should be 2m plus 1, okay, sorry, here I did plus 1, not -1, okay, it's the same, it's gonna be even again, never mind, okay, lambda divided by 2d, okay, that's what I get. And I can again do the same idea I did here, right? It's the same triangle, I can do whatever I want, okay? So this one is actually xm divided by L. Why? Because I said it's like a tangent theta. So I can do this equal to that plus 1 lambda 2d, okay? And right now I can multiply by L, so xm equal to L, 2m plus 1, right? L2m plus 1 lambda 2d. So this is the final result, and this is not a big M, a small m, because it's present a minima, a place of completely darkness. Okay? Perfect, this is the result. Wonderful job, guys. Okay, so right now I want to go to the second part of the question. Right now we did a basic idea. All the equations that we had along the way should be a really basic important equation, and now I want to fuck up the things a little bit, okay, to make it a little bit complicated. So the things that I want to tell you is, right now there was a little bit rain, okay, and one drop of water fall on the exit of one of the slits, okay? That's what's going to happen. So this is the slit, right? Here it is. And here there's a water drop that fall here. The water drop is not that big, okay? It's going to be L. And L is going to be smaller than the delta R. A really small droplet here, okay? And the laser want to point at a direction that's taking you. Want to point the direction P, the same concept that it was before, same P, but right now it's need to move through the water, okay? And here we had this assumption, this is 90 degrees, right? And this distance is delta R, right? And we give the data delta R is bigger than L, okay? And we need to think about that, okay? So that's the idea. Perfect. And what I want to ask you is, what is the velocity of the electric field of the beam inside the droplet, okay? And now it's taking us back to the first question that we talked about, okay? So what's happened? So we know that the speed of light is c, right? C lambda f, okay? But this is the highest speed you can talk about it, okay, in the world. There's no higher speed than that. And this is the speed of light in a vacuum. Really important to note this. Air is not a vacuum, okay? Vacuum is in space. Here on Earth you have air, okay? So it's not actually C. It's kind of a little bit smaller because it's in air, okay? So what actually changed is lambda. We put this index here, okay? And this index here multiplied by f, okay? So this is a correction you need to do. And what is this n? This n actually tell you in which medium you are in, okay? Let's talk about a little bit about this n. This is n, okay? This is gonna be some material, okay? Some material. So if there is no material, vacuum, so n is equal to 1. Okay, so n gonna be 1. But if you're gonna do some interesting material, for example air, so it's not gonna be 1, it's gonna be a little bit bigger than 1. It's gonna be 1.000, I think 0 something, okay? I don't sure what, but it's gonna be 0 something, okay? It's a something, 0 something, a little bit bigger than 1, but usually it's a good approximation to say that air is 1. And this, and let's say talk about water. So water is actually 1.3. Oh man, this is significant. 1.3 is you start to notice it, okay? And glass is even more. Glass is 1.5. So what this n do, okay? So think about it, that the wavelength is actually tell you how the wave look like, how it's propagated in space. So if you propagate in air, it's fun and cool, but then if you enter a place of mud, it's really hard for you to move. So it's not that easy to complete a cycle again and move that long distance. So the light is kind of becoming condensed here. You see what's happened here? And then when you're going to go out, it's going to be at the same wavelength as before. So in this space, let's say it was glass or water or mud or something, so we need to have a new definition to the lambda. The lambda is actually, in this space, the lambda is lambda n, and it's equal to lambda, okay, divided by n. Okay, let's do it bigger. So this distance here inside the material is lambda n equal to the original lambda divided by n. What's that gonna do? If this was the original lambda, it's gonna make it smaller. You see, I'm gonna divide by something that is bigger than 1. Okay? That's the idea. Something that is bigger than 1. So what it's gonna do to the speed, if you think about it, let's draw it here. So let's draw it here in the beginning. So this one is actually equal to what? So Vn is equal to lambda over n multiplied by f. But this is the speed of light. So you see the speed of light also, okay, it's not the speed of light, it's something smaller than the speed of light. Okay, and what we can say about k, remember k? K was 2 pi over lambda, okay? So k going to get bigger, lambda, and the n gonna pop up here, divided by n, so n is here. So k is actually getting bigger, okay? So that's what's gonna happen if you go inside the medium, okay? So how this affect our equation, okay? Let's talk about it. We had a small summary about this diffraction index. Okay, perfect. So, my question to you is to talk about 2 paths, okay? The optic path and the geometry path. What do I mean by that? Let's complete this table. So let's do a table. So this is gonna be geometry. Okay, and geometry is what I see. That's what I see. That's what I see. That's what's happening. And the optic. And optic is how the light gonna see it. That's the idea. That's how I think about it. Okay, this is how the light gonna see it. So this is gonna be. Let's give it all the points names. Okay, so if this is the location P. So we already gave it P. So this is gonna be F. Okay, this is gonna be this is F, this is C, this is E. Okay, so I just gotta give it a name. So if we're gonna talk about if I want to talk about this one, I want to talk about what is E to P, right? And what is C to P, what is each distance. Okay, so the geometry would say this is R1. Okay, this is R1, it's equal to EP. This is the distance that I'm gonna measure. And if I'm gonna look here, what I'm gonna see, first of all, okay, it's R2, this is the distance. Let's give it a little bit more space. This is R1, R2, okay. First of all, I'm gonna go through the drop. So I'm gonna go L. And then I'm gonna go to what left of dr minus L, okay? And then I need to finish this part, which is FP. But we said before that FP is approximately equal to EP, okay? So this one we can say it's almost EP. It's okay to say it, okay? But what's happening when we look at the optic, okay? When the material property actually affect us. So EP going through what? Through air. So the equation is in N multiplied by EP. And air is approximately 1. It's okay. Good. But what's going to happen when I go through the droplet? Right now it's changing. Okay. The R1 is going to move all the time. So what's going to happen? Okay. So when I go through the droplet, I'm not 1. There's some index, okay? We talked about that water is 1.3 approximately. So you have this N over here, plus, and there in this zone, it's delta R minus L plus EP, right? We said that FP is equal to FP, and this one is through air. So this one can be multiplied by 1. Multiplied by 1. Plus, we said it's L multiplied by N. So this one is okay, you're going through air. So you see the difference? This index actually fixes the equation. Here, you succeed to do more. That's what I want to see. Okay, so this, if this is the laser, he get to the water, and he was really condensed, and then he went out really big wavelength, right? This is the wavelength here. Oh my god, this is the wavelength here. Look how small it is. Okay, so they actually open some change between them. That's what happened. Okay, let's talk about the change. So what is delta? Let's talk about the delta in the distance. Okay, so what is the delta between both of them, this one and this one? So we can do from here, we can talk about what is delta x, the difference in the trajectory, the path that they did, as a geometry point of view. So the geometry point of view, if I'm gonna subtract that from that, so I'm gonna left with EP gonna fall out, right? This is gonna fall with this one. Here L gonna fall with this one, and I'm gonna stay with delta R. So we said this is actually what the difference between the two paths. But if I'm gonna look at the optic point of view, what I'm gonna see? EP and EP gonna fall out, but here L would not fall out. You see it? Where are we gonna stay? We're gonna stay with L and minus 1 plus delta R. So we actually got an extra term, this term. You see? This term. We got this extra term going through the droplet. Here, that's what's going on. Okay? So if we're gonna go back to my original equation, if we're gonna say, where is the new actually maximum gonna be at, right? So let's clean this part. We don't need this table anymore. So if you're gonna clean this one, okay? So we're actually gonna see that we talked about that cosines, that E, let's do a reminder, E equal to 2 is 0 because I have two beams. Sinus something that I don't really care, which is changing time. I don't care about it, but multiplied by cosines of what? Cosines of K. Cosines of K. Delta R, I do here a star, that's what we have before, 2. But right now, the real delta R that we have, it's not the geometry path, because we have here contribution of something that was not in vacuum. So this one should be fixed to what? To cosines K to this term. Let's do it in different color. Okay, L n minus 1, let's do it here. L n minus 1 plus the original delta R that we know from before. Okay, so things got a little bit complicated. That's what I want you to see. That's the idea, okay? And if I want to clear this one, I want it to be 1, which means I want to see the light. I want to see the brightest point. Listen, right now I need to solve it. The way to solve it does not change. The only thing that changes, I need to take with me this n all the way. So right now, K, L, n minus 1 plus delta R divided by 2, right? Now this one is equal to where I have the maximum. The maximum I have at m multiplied by pi. So that's the idea. And let's find the xm. Okay, let's find where it's going to be the maxima. So to find that, okay, I can put delta R here. It's not changed. You see this triangle did not die. So this delta R is still the original idea that we have before, which is d sinus theta. And we talked about theta m, the maxima. And k, I know what k it is. It's 2 pi over lambda. Okay, so get rid of this and this. The 2 die here, right? I stay with the lambda. I have this d, this sinus. And I can change the sinus to what? Remember? I can say it's like a tangent theta. And tangent theta equal to xm divided by L. We see the tangents, right? So I can use all the information here and get that xm for the new configuration with the droplet is actually L over D, okay, 2, sorry, not 2, lambda m plus L 1 minus m. So that is the final term, okay, and Okay, let's do the last question. The last question, actually a good one. So, you see that at the beginning everything was symmetrical, right? Let's do it like this. See, look at the laser. So everything was symmetrical. This is here where the laser is pointing. But right now when I put the droplet, stuff did not symmetric anymore, okay? So the stuff are not symmetric anymore because one have the droplet and one not have the droplet. So if I'm gonna draw the laser, this is the laser, right? And it's shining. Sorry. It's the laser and it's shining the direction, right, to the board. So we're gonna be the brightest light. So we know the brightest light should be in the point, if it was symmetrical, that it's the shortest way for both of the laser. For example, for here, for example, that direction, it's the shortest for that one, but not for that slit. It's really long way. But if they both gonna do the same thing, so this is gonna be the brightest point, sorry, if this was the board in the middle, the brightest point is gonna be in the middle. Now it's not symmetrical, right? So we're gonna be the brightest point, and my question to you if it's gonna be positive or negative to compared to this line, this, let's call it X. Is it gonna be positive or negative? So what you're gonna do, we can put M equal to 0, which give us the middle point, right? It's not if this is the light, and then this one, and then this one, and then this one, and this is the brightest light. Okay, this is the center, right? And then I'm gonna have +1, and then I'm gonna have +2, right? This is the location of the brightest light. And this one is the symmetrical, right? -1. So this is gonna be -2. So right now when I'm gonna put M equals 0, I'm not gonna get XM equals 0. It's not gonna be in the middle. Let's find out. So if this is 0, this dying out, and we have L multiplied by L, 1 minus N divided by D. So what's gonna see? We talked about N before. We said that N must be bigger than 1, right? So this is a negative. So if we're gonna put here the droplet, apparently the bigger maximum gonna be a little bit off the line, okay? So guys, before I'm gonna continue on to the last thing, I want you to see the end of the video, okay? Which is gonna give you the idea what's happened if we're not taking a particle or a light, okay? A light, yes. What's happened when we take an electron? So you're gonna press the button.
So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. and it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Hi guys, glad to have you back. Yeah, it was crazy and electrons are really behave in a strange way, but I don't gonna steal the show, and this specific subject go to the next class, which is Physics 3, not Physics 1, not Physics 2, Physics 3, the crazy quantum world. And we finished the class today. Okay, this is the final tutorial. I had the pleasure to teach you during this crazy Corona time. If the video helped you, I would appreciate you to do a like, leave a comment. If you have any question, I really enjoyed to give you this lecture, so comment below and I will answer your question. It was a pleasure to teach you, and hopefully we're gonna go back to the class, to the halls, and we're gonna see each other and not talking only in the internet. But for that time, I was really enjoy to give you this class, this opportunity. Have fun, good luck with the last homework, see you at the exam, good luck, and I recommend you to continue to Physics 3. Okay, good luck, thank you.